Okay, so let's see here. All right, we left off at this question 5.24. Says draw all the possible stereoisomers for each of the following compounds. Each possible stereoisomer should be drawn only once. Well, let's see here. We've got a carbon that's attached to 4 different things here, and we've got a carbon that's attached to 4 different things here. So we have 2 possible stereocenters. Now, if we use that formula that I taught you, which is found in the book, the maximum number of stereoisomers is 2 to the power of n, where n is the number of stereocenters. Then for the first question, question A, you'd have 2 to the power of 2, which would mean a total of 4 compounds. Did anybody get 4 compounds or a different number? How many stereoisomers did anybody wants to throw that out there? Did anybody get an answer for a number of stereoisomers? Well, let's take a look here. What would happen if we put the first methyl going up and we put the other methyl group going down like that? So maybe I could fix that a little bit, but something like this. Could we draw an enantiomer of this compound? The answer is absolutely we can. We have the methyl going up on the top, the methyl going down on the bottom, but we could draw its mirror image, right? We could swap both of those stereocenters. Oops. So let me just do that. So now I have this bond going down and this bond coming up. So I have a pair of enantiomers. And then what's my other option? I could also draw an isomer where I have both of the methyl groups pointing up. So I have this one pointing up like that, and then I have this one pointing up. So those are all stereoisomers of each other. Of course, this compound that I have here, this is a diastereomer. Diastereomer of this compound and this compound, but that's neither here nor there. It's just a different stereoisomer. So let me ask you, what if I drew this compound? Would this be a new stereoisomer if I put both of the methyl groups pointing down? Is this a new stereoisomer, yes or no? Could anybody answer that? Would this be a new stereoisomer? Absolutely, yes. Thanks, Kiana. The answer is no, because this is same as this compound. Those are both cis-1,2-dimethyl cyclohexane. And so we only have 3 possible stereoisomers for this compound. And the reason why these are both the same is because this compound is a meso compound. It does have 2 chiral centers. However, it also has a plane of symmetry running down the molecule. If you rotate this 180 degrees, you end up with the same molecule. And so you only have 3 possible stereoisomers for compound A. Let's try the next one. So I'll go over to a blank document just so I have enough blank space. So let's see here. So this is 5.24b. And they give us this compound where we have a hydroxyl up here and a hydroxyl over here. Well, we have 2 stereocenters, 1, 2. So we might think 2 to the power of 2 gives me 4 possible stereoisomers. So let's try drawing some stereoisomers. We could have something like this, where we have one hydroxyl coming up and the other hydroxyl group pointing down. And of course, we could have its enantiomer. So if I just copy and paste this compound, one option, instead of redrawing it, if you have an iPad or a Surface or a tablet, would be just to take the compound and put it here. And whatever is a wedge, I'll erase that. And whatever is a dash, I'll erase that. And I'll just swap them. So now I have a dash here, and I have a wedge here. And these 2 compounds are enantiomers. Enantiomers. Now, what if I drew a compound? Let's see here, if I pasted this, what if I had an isomer where I have both of the hydroxyl is pointing up. So let's erase this dash and we'll replace it with a wedge like this. Now, could I draw another isomer where I have both of them pointing down? With the one in black and the one in blue, are these stereoisomers of one another? The answer is no. These are the same. Why? Because we have a plane of symmetry running down this molecule, and thus this is a meso compound. And so we only end up with this pair of enantiomers and this other diastereomer to each one of those enantiomers, which happens to be a meso compound, and therefore I only have 3 possible stereoisomers for this compound, just like I did in A. Any questions about meso compounds before we move on? And of course, you're going to have to run some practice on that. There's nobody who could master that without a little bit of practice. Okay, well, let's go back to where we were, somewhere down here. Okay, we already discussed plane polarized light, and now we're going to move on to Fischer projections. Fischer projections, and you might have seen a Fischer projection of something like glucose in your biology textbook, and I know that many of you have already taken biology, so you might see something drawn like this in your biology textbook where they have, let me just draw it in here, this compound drawn in this manner, and this is called D-glucose. It's the naturally occurring form of glucose. So you might see that in your biology textbook, but we're going to talk about this in a second. In where the Fischer projection comes from, these kinds of structures like this or like this, they come from the fact that Emil Fischer, back in the late 1800s, was isolating all kinds of sugars and other naturally occurring compounds. They had multiple stereocenters. We're talking like, more than 2 stereocenters. Oftentimes you'd have 4 or 5 stereocenters. And so he was trying to find a way to draw these compounds quickly and quickly assess, are these compounds diastereomers? Are they enantiomers? Et cetera, et cetera. And so he developed the Fischer projection for that purpose. When you look at a Fischer projection with all these lines on it, just like this compound here, what you need to know as an organic chemist or an organic chemistry student is that the lines that are horizontal are coming out towards you. They are essentially on wedges. We don't draw this as a wedge, but it's implied that they are coming out towards you like they're going to hug you. This is an idea that my students gave me years ago, and I always thought it was funny. And then whatever lines are vertical, those are as if they are dashes, and so they are going back into the page. But let's say we wanted to designate the chirality at this carbon, which is certainly chiral. What do you notice about the hydrogen? Well, the hydrogen is the lowest priority group, yet it's coming out towards you. What did we say? If the hydrogen is coming out towards you, you reverse the stereochemistry. And so we would do the same thing for a Fischer projection. Our highest priority group would be the hydroxyl, lowest would be the hydrogen, second would be the ethyl, third would be the methyl. So we go from 1 to 2 to 3, which is clockwise. But again, since our hydrogen is coming out towards us like this, we reverse it, and this stereocenter would be S. And that's the same rationale that we could take for any one of the stereocenters in D-glucose. It wouldn't matter if it's this one, this one, this one, or this one. You can do the same rationale for all of them. So again, Fischer projections are really useful when you're drawing compounds that have multiple chirality centers. This first compound, we would call this an aldotetrose. It has 2 chiral centers. This one has 1, 2, 3. This one has 1, 2, 3, 4. And so again, multiple chirality centers, it gets really helpful to use Fischer projections. Let's get some more practice in designating a stereocenter as R or S in a Fischer projection. Take a look at this one here. If we take a look here, we see the oxygen is number 1, the hydrogen is number 4. This carbon is attached to oxygen, oxygen, hydrogen, whereas this carbon is attached to oxygen, carbon, hydrogen. Here's my tiebreaker. Therefore, this group is going to be number 2. This group would be number 3. I go from 1 to 2 to 3. That's counterclockwise, so that would be S. But remember, the hydrogen is coming out towards you, and so you reverse that. Thus, the stereochemistry here is R. And so let's label that first stereocenter as being R. Could anybody designate the stereochemistry at the next stereocenter? Could anybody tell me, is this one R or S? I'll give you a second to think about it. I'll give you 1 minute to think about it. Hey, Siri, set a timer for 1 minute. And if you think you have the answer,
1 minute.
Go ahead and type it in the chat, or just unmute your mic and yell at the whole class. I think it's this. Anybody have an idea about this one? Must be getting close to a minute. All right, cool. Tracy's got an answer. All right, so time's up. Tracy, I think you're 100% correct. I think you are 100% correct. Let's take a look. If we look at this stereocenter, the oxygen is 1, the hydrogen is 4. This carbon is attached to an oxygen, hydrogen, hydrogen, and this carbon is attached to an oxygen, carbon, hydrogen. This is my tiebreaker. Therefore, this is number 2. This is number 3. I go from 1 to 2 to 3, which is clockwise. However, my hydrogen is coming out in front. And so, Tracy, you are 100% correct. It is S. And there you have it. That is the same rationale you would take for any of the chiral centers in a Fischer projection. And again, another advantage to Fischer projections, and I think I said this very quickly, is that they really enable the viewer to quickly assess stereoisomeric relationships. If you look at these two compounds, you can see that each one of these stereocenters is reversed, as are these two. Thus, these would be enantiomers. Whereas if we look at the other example, you can see that these two are reversed, whereas these ones are not, and therefore they must be diastereomers. They're stereoisomers, but they're not mirror images. So Fischer projections, very, very handy. If anybody studies biology, now it'll help you whenever you see a sugar drawn as a Fischer projection. And also, I'll put this bug in your ear later on. I think it's chapter 24, 23, 24, something like that. I can tell you if I look at the book here quickly. It's chapter 24. So in chapter 24, we talk all about carbohydrate chemistry, just the chemistry of sugars. And so we're going to bring this whole concept back in that chapter in organic chemistry too. Well, if you didn't get that last one, you have a chance to redeem yourself. Let's tackle these two and see if we can determine the stereochemistry at either of these. The first one is an amino acid. So let's see here. We have our chiral center. We have a carbon, a nitrogen, a hydrogen, and another carbon. Which one of those elements has the highest atomic number? Which one would have the highest priority out of those 4 atoms? Anybody tell me which one of these has the highest atomic number? You always want to have a periodic table with you when you're studying organic chemistry. Good, thanks, Tracy. So the nitrogen is number 1. The hydrogen is number 4. Hydrogen has the lowest atomic number on the periodic table. Thus, it has to be number 4. But if we look at the 2 carbons, the carbon on the top is attached to oxygen, 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 right? 1, 2, 3 bonds to oxygen. The carbon on the bottom is attached to an oxygen and 2 hydrogens, H, H. Therefore, this is my tiebreaker, and the carboxyl group on the top is going to be the second highest priority, and all of this down here would be the third highest priority. Remember, you go from 1 to 2 to 3 around the chiral center. So we're going counterclockwise. And counterclockwise is normally S, but remember this hydrogen is horizontal, therefore it's coming out towards you. And so we reverse this, and the stereochemistry is R. Let's take a look at this one on the bottom. I'm going to go a little faster this time. We have the hydroxyl. This oxygen is going to be number 1. The hydrogen is number 4. This carbon is attached to 3 hydrogen atoms. And this carbon is attached to 2 oxygens and a hydrogen. Here's our tiebreaker, 1, 2, and 3. So we go 1, 2, 3. We're going clockwise. Remember, the hydrogen is coming out towards you, so you reverse that. So it's not R, but this stereocenter is S. And there you have it. Fischer projections and assigning stereochemical configurations at chiral centers in a Fischer projection. Section 5.8 is kind of an interesting section. It deals with what are called conformationally mobile compounds. I just want to kind of go over it with you quickly just so you have a rough idea of what it's talking about. You're going to have to go and read it yourself. And good news is it's a very short section. You can read it in probably 3 minutes. It's not very long at all. Because there are some concepts in here that I think a student needs to really look at themselves in order to comprehend what the heck is going on here. But let's take a look here. It says, we know that molecules can rotate around single bonds. There's no new news there for us. Let's imagine you had butane, and that's the focus of this slide, right? This is butane and this is butane. Well, let's imagine you have butane. You know that you have rotation around the carbon 2-3 bond. So we have 1, 2, 3, 4. We know we have free rotation around a single bond. And we know that if we draw a Newman projection looking down the carbon 2-3 axis, we end up with 2 gauche conformations. Right? There's 2 gauche conformations where the dihedral angle here, of course, is 60 degrees. Right? But these 2 gauche conformations, they're not superimposable, are they? You see what I'm saying? If I was to take this molecule, or this conformation, I should say, and try to plop it on top of here, this methyl group in green, that would end up over here. So these 2 conformations, are you ready for this? Whoa. These 2 conformations are actually enantiomeric. The conformations are enantiomers of each other. Now hold the phone. Keep in mind that this arrow means that these 2 conformations are in equilibrium with each other. So because these 2 compounds are actually what we call rotamers, which means they're interchangeable by rotation of a bond, butane is not a chiral compound. So we have chiral rotamers of each other, or we could say that these 2 conformations are enantiomers of each other, but since there's free rotation, they cancel each other out in the end, and butane is not a chiral molecule. There's no chiral center in the molecule. Now, another interesting example is what if you look at the 2 chair conformations of cis 1,2-dimethyl cyclohexene. You see that this methyl is going up an axial, this one is equatorial, and then we flip the ring, then we have this methyl going up an axial and this one going up an equatorial. Now that's flipping the ring. And if you were to take and draw this compound, so I'll try to draw it the best I can, and Mr. Dion isn't the cat's meow, but at doing this, but I'll do my best. If I take this compound, which is the enantiomer, and if I was to spin that around, so let me try to do it like this. If I was to try to take an axis through here, and if I was to try to spin this 180 degrees, then what would you end up with? You'd end up with this right here, where you'd have, sorry, I drew it the wrong way. I think I'm making this more complex than it needs to be. So you would actually end up with, no. I'm making this more complicated than it needs to be. The bottom line is you can't take, so what I was originally trying to say, which is probably the easiest to explain it, if you take this compound and you try to plop it on top of the other one. So if we take this compound and try to plop it on here, we can't do that, right? So they're non-superimposable mirror images of each other. Okay, I think that's a lot clearer. You can clearly see that they're mirror images, and hopefully you can all clearly see that you can't take this and plop it on top of that. And so these are also enantiomers of each other. However, you know that this is not a chiral compound, and how do you know that? Well, the Sparks Notes version is this. What you would want to do is you would want to draw either a Haworth projection like this, or you would either want to draw the compound just using dashes and wedges. And when you do that, you see that there is a plane of symmetry. And so sometimes if we use a chair, it's not going to be, the easiest way to assess whether a compound is achiral or not. Sometimes it's better to draw it as a Haworth projection or using just dashes and wedges. That's a lot of explanation, probably more than I need to give. Anyhow, sections 5.9 and 5.10, we skip those. So don't worry about chirality without chirality centers or resolution of enantiomers. But of course, it's always FYI. If you want to read that for your own information, I highly recommend it. There's always some interesting content in there. And that brings us on this cold, raining outside, I don't know, but this cold, damp Thursday morning to the last section of chapter 5, which is E and Z designations for alkenes. Remember how I showed you cis and trans? And we actually talked about cis and trans at the very beginning of our lecture today. Let's imagine you have, this compound, right? You've got, two groups that are opposite each other. We call that trans. And then if we have two groups that are on the same side as each other, we call that cis. Well, one thing that you got to remember about that is cis and trans can only be used when you have groups that are exactly the same. Okay? Otherwise, you can't use cis and trans. But if you look at these two compounds that I have here, you see that these are not, they're non-identical compounds, are they? Right? These are two diastereomers. Why? They're stereoisomers, but they're not enantiomers. You can't take this compound and plop it on top of this one. So we have a pair of diastereomers, but you cannot use cis and trans for these because you don't have a like group on each carbon of the alkene. You've got 4 different groups. You've got this ethyl group, you've got an amino group, you've got a hydrogen, and you've got a fluorine. 4 different groups, but again, these two compounds are diastereomers of each other, and we can't use trans or cis, so what do? We use E and Z. Well, good news is you can apply the Kahn-Ingold Prelog rules in order to designate a compound as being E or Z. Here's how we do it. In order to assign a double bond as being E or Z, what we do is we prioritize the groups on the carbon-carbon double bond based on their atomic number. Here, on this carbon that I'm highlighting in black, we have the fluorine in red, and then we have a carbon in blue. Carbon has an atomic number of 6. Fluorine has an atomic number of 9. And so fluorine is going to take higher priority. I'll highlight that in yellow. If we look at the 2 other atoms using the same rationale, nitrogen has a higher priority than hydrogen. Since those are on the same side, we say that this is a Z isomer. Z stands for zusammen, and I don't know if I'm spelling that correctly, which in German means together. Okay, like that. So they're on the same side. Sometimes my students will say they're on the same side. I don't know. It's just a way of remembering it. It's kind of a mnemonic that students have developed over the years. Now, if you look at the other compound, it's E or entgegen. Oh, I did spell it correctly, which means opposite. And sometimes my students will say E for eposit. And again, this is just a silly mnemonic that my students came up with. But hey, if it helps you remember, I don't care. So we look at the compound. You have the fluorine on this side. You have the nitrogen on this side. They're eposit or E. And so we end up with an E alkene. And so there you go. We've learned how to assign compounds as being cis and trans, but now you know the difference between E and Z. Question 5.29 says, for each of the following alkenes, assign the configuration of the double bond as either E or Z. So let's see here. All right, let's take a look at the first one. And is this E or Z? Let's see. On this carbon in blue, we've got an isopropyl, and then we've got a butyl. And on this carbon in red, we've got a hydrogen, which isn't drawn. I'll put it in here. And then we have this isobutyl group. So let's start with let's start with the carbon in blue. If I look at this carbon, it's attached to carbon, carbon, hydrogen, whereas this carbon is attached to carbon, hydrogen, hydrogen. Therefore, this is the tiebreaker, and this isopropyl group is going to have a higher priority than the butyl group. If I go on the other side, well, you have a hydrogen and an isobutyl. Well, hopefully you realize that the isobutyl is going to be higher priority because this is a carbon. Since those two groups that I have in the green and the blue big circles are on opposite sides, we say that this is an E alkene. And let's look at the one on the bottom. Could anybody assign this one? Could anybody tell me? Would the one on the bottom be E or Z? I'll draw the hydrogen in here. Does anybody have an idea about the one on the bottom, D? Yeah, I think that my students are right. Thanks, Tracy. If we look at the carbon on the left, we see that the chlorine has a higher priority than a carbon. And if we look at the carbon on the right, the one I'm highlighting in green, well, anything takes precedence over a hydrogen. And so the carbon takes higher priority. Oops, let me try to be somewhat consistent. And those are on the ZAME side. So ZAME or Z. These are zusammen, together. And there you have it, my friends, E and Z, and cis and trans. You know, sometimes, or one time a student asked me, you know, can you have a compound that's trans and Z? Is that, you know, or, you know, could you have a compound that's cis and E? Is that possible? The answer is yeah. If you look at something kind of wacky, not wacky, but if you look at a compound like this, let's imagine you had this compound, but then you have a chlorine over here, right? You have a methyl group here and a methyl group here. So the compound is trans, okay? Or if you look at what's attached to the two carbons, here you have a hydrogen. So the methyl is higher priority, and then you have a chlorine over here. So you could call it also a Z compound. So you can have compounds that are trans, and it could be Z, or the other way around. It could be cis and E. But we're not going to stress about that a whole lot. I'm either going to ask you, is it E or Z or cis or trans? But the bottom line is we usually use E and Z when we can't use cis or trans. That's normally when we use it. But you've got to be aware that you can use it. If you have a compound that is cis or trans, you can use E or Z. That will work too. And that brings us to the end of chapter 5. The entire thing, the whole kit and caboodle, so to speak.